Hey, good afternoon, everybody. Okay, welcome to another segment of physics lesson with Papa Lim. Okay, you like my wallpaper? Yeah, not bad. It's quite delicious. Okay, ice cream with on toast. Okay, without any distraction. Okay, today we'll be looking at section 2 of kinematics 2.2, which is speed and velocity. Okay, so here we go. All right. Okay. Now, in this section here, we look at speed and velocity. Okay. Then after that, we end it off with acceleration. Okay. Speed and velocity is another classic example of scalar and vector. Okay, like what we mentioned in the last segment. Okay, scalar and vector. Speed and velocity is another one, another classic example. Okay, speed is what we know as the how fast the object is going. That information is what we call speed. Okay, for speed wise, it's considered a scalar. Okay, because it only has magnitude. For example, 20 meter per second. Okay, so this information will tell us that the how fast 20 meter per second, but it has no sense of direction to say whether it's left, right, up, or down. Okay, so this is considered what we mean as a scalar. But for velocity is what we mean by a vector with direction. So vector, when we say it's a vector, it means it has magnitude and it has direction. Okay, so example, positive 20 meter per second. So positive 20 meter per second. This information, the positive, it could actually denotes direction. It could means that is actually the object is actually traveling 20 meter per second to the right. Okay, to the right, or it can be actually traveling 20 meter to the upwards. Okay, so the positive sign, the sign plus or minus actually tell us the directions. Okay, but they are just, it's just, I would say that they give different informations, but ultimately the information they as in the quantity they are representing is how fast the object is moving. So that's why they both have the same units, which is meter per second. Okay, and definition of speed, like we all learned in primary school, is a speed change in distance by time, or change in distance per unit time. Okay, since it's a scalar, so distance will be a scalar also. But for velocity, because it is a vector, so when you talk about change in distance, it has to have a direction in it. And when you say distance with direction, it's actually called displacement. So the definition that we look at is actually what we call the change of displacement per unit time. Or sometimes we say change or in direction, okay, or change in distance plus direction per unit time. So that's what we mean by displacement. Okay. Now, velocity, okay, is a vector quantity like I mentioned before. It has certain directions. Okay, so when we talk about velocity, it has magnitude and direction. When we say velocity changes, it doesn't mean the number change. Okay, it could means that, okay, it could mean that the direction, okay, could be changing. The direction could change. The magnitude could remain constant. Okay, it doesn't mean it has to be the magnitude changing. Magnitude changing the direction. Constant. No, it can be any number. Okay, remember, because velocity consists of magnitude and direction. Any one of these component, okay, changes, the vector or the velocity will change. Okay, so for example, okay, if I have in terms of magnitude is 5 meter per second, okay, but now what happened is I change my direction. Okay, so overall the information I'm trying to portray, the 5 meter east and 5 meter per second east, 5 meter per second north, together this information is what we call velocity. And with the change in direction, I will say that the velocity of the object actually, or the car has actually changed. Okay. Now, another aspect that we have is we like to use the word constant. Okay, so if the directions and the magnitude remain the same, we have what we call constant velocity, or what we call uniform velocity. Okay, so same, what we call same velocity. Now, average speed and average velocity. Okay, average speed, like we mentioned in like primary school, okay, or even set one, we are looking at total distance divided by total time. Okay, total time here refer to the journey. Total distance traveled is the physical distance traveled by the car or by the object. Velocity, okay, can also changes. Velocity, okay, average velocity is the change in distance with directions, or what we call displacements. Okay, remember displacement here, total displacement here may or may not refer to the actual distance traveled. Important thing like what you mentioned in 2.1, where displacement is always the shortest line. Okay, what line? Straight line. Okay, and it is always between start to end. Okay, so the shorter distance between start to end, I may or may not physically travel that particular path, but that will be my displacement. The shortest line between start and end divided by the total time taken for the entire journey. And this ratio is what we call average velocity. Okay. Now, for speed, the same thing as we all encountered before, average speed is not a fixed number. Right? Likewise, for average velocity, it's not a fixed number. It changes from time to time, changes from the amount of displacement amount of distance I travel and then time taken. So speed, average speed, okay, across the journey, half the journey, or even a quarter of the journey, okay, average speed will change. Okay, so it doesn't have to be a fixed number. Okay. Now, for example, okay, speed and velocity. Remember, speed. Okay, speed is the actual path I travel. Velocity is the shortest line between start and end. Okay, so now average speed is total distance divided by total time. Okay, so total distance, whether it's blue or red path. Okay, let's say I use the blue one. Okay, so this is blue path. Okay, the blue path is 7 kilometers. Total time travel by this particular guy is half an hour. Okay, it's actually going quite slow. Yeah, actually. Okay, quite slow actually. So the average speed will be 14 kilometers per hour. Okay, if I'm looking at displacement, okay, if I take A as the starting point, B as the ending point, okay, if I look at the displacement, it will be the shortest distance between these two lines. The displacement will actually be 5 kilometers. Okay, 5 kilometers, but remember, if you look at the context, 5 kilometers is actually not the actual path I travel. Okay, it's just the shortest line. Okay, time taken is half an hour. Half an hour, this is the time taken, physical time I've taken, which is half an hour. Okay, for the entire journey, regardless of path. Okay, because the question say, I take half an hour. Okay, so now if you do the math, you'll find that the average velocity is looking at is 10 kilometers per hour. Okay, so you'll find that if you do the calculations correctly, sometimes it is most often that the average velocity and the average speed actually end up to be a different number. Okay, because the information that is input to that formula or input that's average velocity or the average speed is trying to portray, the information they're trying to portray is actually different. Okay, so it's just that both of them are actually measuring how fast the object is moving, but average velocity take into account of change in directions and the direction involved. Okay, and take into consideration of the path, the shortest line between the path between start and end point. So I would say that although they're trying to portray the same data information, which is how fast the object is moving, because the information portrayed is different, so that's why the number appearing in your calculations may or may not be the same. Okay, so students, you have to take note of the slight distinctions between velocity and speed, or what we call scalar versus vector. The other extent that we have is what we call acceleration. Acceleration is a scale, it's definitely a vector. Okay, it talk about how fast my velocity change. Okay, in this case, it's not how fast I go, it's how fast my speed change. I am more interested in how fast my speed change in each unit of second. Okay, so in this case, the context or the information that I'm trying to portray when I have acceleration, when I uses the accelerations, the first clear information I'm trying to tell people is that with accelerations, I'm actually trying to tell you how fast actually my speed changes. Okay, so the main focus is not how fast I have been moving, it's how fast my speed has changed. Okay, that's what we mean by acceleration, or the change in velocity per unit time. Okay, so in this context, is speed, velocity divided by time is meter per second per second. This is speed. Okay, sorry, this is velocity. Okay, change per unit time. So you have meter per second, which is meter per second square. Okay, so acceleration actually tell us how fast the speed change. Okay, that information, does it tell the audience, does it tell the people how fast is the person going? Depends on information. So it's not a direct information. Once I give you acceleration, that data, that number, it doesn't tell you how fast. It does tell you, but it's not direct. The direct information I'm trying to tell you is actually how fast my speed has changed. It could be I have changed like 10 meters per second. We have changed 10 meters per second in that 1 minute. Or I might change actually 0.1 meter per second, maybe across a time interval of 0.1 second. So I will end up with maybe a change in 10 meter per second square, acceleration of 10 meter per second square. But 10 meter per second square tell us how fast my speed changed. But has I been going very fast? Okay, that information is still unknown. Okay, so the first tier of the information for acceleration, it tells us how fast my speed changed. Whether am I going fast or slow, it depends on your calculations at the second tier. Okay, so students, you have to make a slight distinction between velocity and acceleration. They are talking about the same object, the same pictures, but they're analyzing the object or the story at different platform or different theory. Okay, for example, in this case, okay, I start with 5 meters per second. Okay, due is okay, so this is my velocity. I change my speed. Okay, I change my speed from 5 meters per second to 10 meters per second, same directions. Okay, there will be accelerations. Okay, there will be accelerations. Okay, because why? I have changed my velocity. I change my velocity. Okay, same thing if I change directions. Okay, 5 meters per second is now I change to 5 meters per second north. This change, it also implies I have an accelerations. Likewise, if I have change in speed from 5 meters per second, I change to 10 meters per second. Direction, I change from east to north. This will also imply that I have an accelerations, okay, because my velocity does change. Okay, so if you look at the context, okay, oh yeah, forgot. Did I roughly go through the formula? Yeah, the formula is here. Okay, so if you look at context-wise in theory, the acceleration is known as the rate of change of velocity. So there are different types of acceleration. I can have constant acceleration, which is commonly known as uniform acceleration, or I can have increasing acceleration, decreasing acceleration, or I can have even have decelerations. So it depends on what the story or what the context you are looking at. But in general, acceleration is governed by one formula, which is change, which what we mentioned, the change in your velocity per unit time. Change your velocity, I can further break it down into change, usually we refer to final, okay, velocity minus initial velocity. Okay, so this is the context that you must be careful. Okay, final minus initial. Okay, divided by same thing, final time minus initial time. Okay, so the context that we are looking at, we always take the final first, then we take with reference to the initial. Okay, so this is the mathematical formula to it. Okay, so example, if I use the formula, or later I will show you. Okay, then after you come up with a number, that number will represent the acceleration of the object. Okay, now, for example, now let's say we look at the math. Okay, now I start out with 20 meters per second. So let's say in terms of context, this is 1 second. Okay, so I change 20 meters per second, my speed, my velocity changes 20 meters per second in 1 second. Okay, so if you look at the change in speed, initial speed is 20 meters per second, final speed is initial speed is 0 meters per second, final speed is 20 meters per second. So if I look at the formula, acceleration will be 20 final minus initial divided by time taken. Time taken here is 1 second. So the acceleration of the object will be 20 meters per second square. Okay, so it has tell me this information tell me that the speed actually changes 20 meters per second in 1 second. Similarly, if I have constant acceleration, which is acceleration remaining the same, okay, constant acceleration or what we call uniform acceleration, it will mean that the speed will actually change another 20 meters per second in the same context of 1 second. This is what we mean by constant acceleration. The acceleration of the object actually changes. It's actually the same, imply the speed actually changes the same amount each time. This is what we mean by constant accelerations. Okay. Now, what happens is now if I have negative acceleration, okay. So let's take a look at this. Okay. So now same thing. I start with 60 meters per second. This is my initial. Okay. My speed dropped by 20 meters per second in 1 second. Okay. So if you look at the formula, acceleration is actually final minus initial divided by time. Final speed is 40 meters per second. This is my final. So it's 40 meters per second. Divided by initial speed, which is 40. Oh, sorry, which is 60. My mistake. Okay. Now 60 meters per second in 1 second. So you'll find that if you do the math, you'll find that the acceleration now is actually negative 20 meters per second square. Okay, this number is actually this number, what is it trying to tell us is that it's trying to tell us that the speed of the object actually drops. Remember, there's a negative sign. Huh? It drops or it reduces by 20 meters per second in 1 second. Okay, so when we say we have a negative acceleration, it actually means the speed slow down at a constant rate. Okay, so the speed will drop down every time. Okay, every 1 second, he will drop by 20. Every 1 meter, he will drop by 20. Okay, this is what we mean by constant negative acceleration. Or sometimes we have a name for it, we call deceleration. Okay. Okay, sometimes we say negative uniform acceleration. I like to replace it with this. The negative acceleration means it is uniform deceleration. Okay, so sometimes we call negative acceleration, okay, to be deceleration. So uniform negative acceleration, it actually means uniform deceleration. Okay, it's just English basically. Yeah, I can just replace it. Now, non-uniform acceleration, same thing. Okay. Okay, it means the speed actually changes. Okay, so for example, 30 meters per second in 1 second. So my acceleration will be 30 meters per second square. So I could have 20 meters per second in 1 second. Okay, so that my A will be 20 meters per second square. So it changes another 20. So it will be plus 20. So it's 50 meters per second. And the speed will change and acceleration will change. Okay, so the acceleration tells us how fast my speed is changing. Okay, so this is the context or this is the meaning behind acceleration. It tells us how the speed actually changes. Okay. Likewise, for deceleration, it can be non-uniform. So negative acceleration, you tell us how fast or how much my speed actually drops in 1 second. Okay. So in terms of context, like I mentioned before, acceleration, it can be positive or negative. Negative acceleration, it can actually be replaced. If you look at English, it can actually replace with the word decelerations. Okay. Or sometimes we have this thing called retardations. Okay, so negative. So if you talk about acceleration, it can be positive. Okay. Example, A equal to 20 meters per second square. Negative acceleration could be A equal to minus 20 meters per second square. Okay, so it's just different way of representing it. The math in English. Okay, so formula wise, we're looking at is formula acceleration is final speed minus initial speed divided by total time taken. Okay. Now, so if you look at acceleration, okay, so if you look at the speed changes from 10 meters per second to 15 meters per second in 1.2. Okay, so remember this is my initial, this is my final speed. Okay, so if I look at acceleration, it's a classic example of final minus initial. Okay, divided by final time minus initial time. So you get, if you pump the number inside, you get the answer straight away. I wouldn't think it's complicated. Just be careful about the math. Okay, if not, okay, so this is where I end off. Okay, for acceleration, speed and velocity. Okay, I talk about the distinction between them, and importantly also the formulas and the meaning behind accelerations. Okay, so before we end, okay, just remember a rule of thumb. Okay, make a distinction between velocity and acceleration. Okay, do not be confused about over these two values. Okay, velocity talk about how fast I move in a certain directions. Acceleration describe or it tell you how fast the speed changes. Okay, he is not about describing the object, whether the object is fast or not. It's telling you how fast the speed is changing. Okay, so there's a slight difference between them. Okay, they are describing different contexts. Okay, the same object, the object is moving, they are describing this object. The velocity tells us how fast the speed is moving. Acceleration tells us how fast the speed is changing. Okay, not about the object. Okay, so if not anything, if I make any mistake, same as before, drop me an email. If anything that you need me to go through in details or you need additional explanation, also drop me a message or drop me a comment at the bottom. Okay, if not, thank you very much. Bye bye.